Have you ever actually stopped to think about the sheer, mind-boggling scale of the internet? I mean, every single second, billions of emails, videos, and texts are just zipping around the globe. But how does a simple photo on your phone actually reach your friend who's thousands of miles away? Well, today, we're going to demystify the magic of data communications. We are going to follow a single, solitary message on its epic journey from creation all the way to its final destination. And let me tell you, it is a hazardous trip. It's full of strict rules, physical highways, real-time translators, and literal forces of nature trying to destroy it. So let's dive right in.
Here's our roadmap for today. We'll start with the basics of data exchange, look at the anatomy of a network, and then talk about choosing the right path. After that, we'll cover the role of modems, the hazards of the journey, and wrap things up with modes of communication.
All right, Section 1, the basics of data exchange.
At its core, data communications is simply the process of exchanging data between devices via some form of transmission medium. Now, what's really crucial to understand here is that this isn't about generating the data. Your camera creates the photo. Data communications is the active, deliberate process of transporting that photo effectively from point A to point B. Think of it like this. It's the delivery service, not the manufacturer.
And this delivery service has 4 incredibly strict rules to be considered successful. First up, delivery. The system literally has to get the data to the correct intended destination. No wrong address is allowed. Second is accuracy. The data must arrive completely altered. A corrupted photo is, well, completely useless to us. Third, timeliness. Data delivered late, especially in things like live video or voice calls, is totally pointless. And fourth is jitter, which is just a fancy way of referring to the variation in packet arrival times. If parts of your video arrive inconsistently, the video stutters. Our traveling message absolutely must satisfy all 4 of these conditions.
Okay, moving on to Section 2, Anatomy of a Network.
Take a look at this. On one side, we have the transmitter, the device sending the message, like your computer. On the other side, the receiver, the device getting the message. Between them is the medium, the physical channel the message travels over. And right in the center of it all is the message itself. But check out those boxes at the bottom labeled protocol. This is perhaps the most invisible piece of the entire puzzle.
So the absolutely crucial point here is that a protocol is a set of rules governing this communication. It's a strict agreement between the communicating devices. Without a protocol, you might have 2 computers perfectly connected by a physical cable, but they still can't communicate. It would be exactly like a person who only speaks German trying to have a conversation with someone who only speaks Japanese. The physical connection is there, but the protocol, the shared language and rules of engagement, is missing.
Section 3, choosing the right path. In the world of networking, roads basically come in 2 flavors, guided and unguided media. Guided media means our message is traveling along a solid, physical, tangible path, like a copper wire or a glass cable. Unguided media, on the other hand, means the message is surfing on invisible, omnidirectional electromagnetic waves right through the air. This is your Wi-Fi, Bluetooth, or satellite signals.
Let's look a little closer at those guided physical highways. We generally have 3 main options. Twisted pair is the most common. It's that cheap copper wiring used pretty much everywhere. Then we have coaxial cable, which has a solid core and heavy shielding, making it much better for transmission. You probably know it from the back of your TV. Finally, the undisputed king, optical fiber. Instead of sending electricity through copper, optical fiber uses a microscopic glass core to transmit data using pulses of light. This absolute revolution allows for mind-boggling speeds, carrying trillions of bits per second without being affected by electromagnetic radiation. It's a total game changer.
Now, what's really interesting here is how the wires inside this twisted pair cable are literally twisted around each other in a double helix. This isn't just to make it look neat. That physical twisting acts as a genius defense mechanism. It protects the wire from external electromagnetic interference, and more importantly, it reduces something called crosstalk. Crosstalk is when a signal leaks from one wire and corrupts the data on the wire right next to it. Simply twisting them together actually fixes the problem. Pretty brilliant, right?
Before we leave our network paths, we have to talk about capacity. There's a perfect analogy for bandwidth here. A narrow range of frequencies is like a garden hose with a small diameter. The flow of water, or in our case information, is highly restricted. Wider bandwidths are like massive water mains, permitting rapid, massive information flow.
Section 4, the role of modems.
We use them every single day, but what actually is a modem? Well, the word itself is really a mashup of 2 words, modulator and demodulator.
Computers speak strictly in digital, just ones and zeros, but traditional phone lines were built to carry analog wave signals, like the human voice. A modem sits right at the border and translates. It modulates your computer's digital signal into an analog sine wave to travel over the wire, and the modem at the other end demodulates that analog wave back into crisp digital ones and zeros.
And these translators come in so many forms today. Some are built directly into your devices, some are external boxes sitting on your desk, and some are wireless, using radio transmitters to keep mobile devices connected on the go. They are the crucial boundary checkpoints for our traveling message.
All right, Section 5, Hazards of the Journey. So, as it turns out, physics is constantly trying to destroy our data in transit. This is called transmission impairment, and it comes from three main enemies: attenuation, distortion, and noise. Attenuation is simply a loss of energy. Just like a shout gets quieter the further away you stand, a signal loses strength over distance. To fix this, we literally have to place amplifiers along the route to boost the signal back up.
Then we have distortion, which literally changes the physical shape of our message. In guided media, different frequencies actually travel at slightly different speeds, so parts of our single message will arrive at the receiver at slightly different times. This is called delay distortion, and as you can see, those varying arrival times warp the clean, composite signal into a messy, out-of-phase wave.
But noise is our most relentless villain. Imagine a beautiful, clean, transmitted signal. Suddenly, an unwanted spike of random noise is injected into the transmission medium. By the time it reaches its destination, our clean wave is scarred and corrupted by that extra energy.
Noise comes in 4 nasty flavors. Thermal noise is caused by the random motion of electrons. It's always there, providing a baseline of white noise. Intermodulation noise happens when equipment malfunctions. We already discussed crosstalk. That's when you accidentally hear a ghostly conversation from another wire. But the deadliest one for our digital data is impulse noise. These are sharp, instantaneous spikes of energy. A 0.01 second spike might just sound like a tiny click on a voice call. But for digital data traveling at high speeds, that tiny click can instantly destroy 50 bits of information.
Finally, Section 6, Modes of Communication.
Even with the absolute perfect cable and protocol, devices still have to agree on a transmission mode. There are 3 options here. Simplex mode means data flows in one direction only. Half-duplex means data can flow in both directions, but they have to take turns, not at the same time. And full duplex means robust, simultaneous two-way communication.
I love this analogy because it makes it immediately understandable. Simplex mode is exactly like an escalator, a doorbell, or a fire alarm. You can only go one way. A TV broadcasting a signal to your antenna is simplex. The TV station sends, you receive. There is absolutely no mechanism for you to send a signal back to the broadcaster through that same circuit.
And that brings our message's incredible journey to a close. We've seen how strict the rules are, how impressive the physical cables are, and the massive physical hazards data has to overcome every single second. So I want to leave you with a question to test your new knowledge. Think about the device you're holding or sitting in front of right now. Which data transmission mode, simplex, half-duplex, or full duplex, are you using to watch this explainer on the internet? Think about it, and I'll catch you in the next one.